So now we're going to take our knowledge of what a weak acid is and a strong acid is, our knowledge about an equilibrium constant for these reactions called the acid ionization constant, and we're going to start doing calculations. We're going to learn how to calculate the pH of strong acids and weak acids. So, two somethings we have to consider. Well, we'll figure out what that word is here in just a minute. In all aqueous solutions of acids, not only is the acid reaction important, reactions, that's what the word is, two reactions we must consider. Not only is the acid reaction important, but also the ionization of water. And we were alluding to that in our last lesson. As you put in the H3O+, its concentration rises while the OH concentration drops. We have to keep those two things in mind. So right now, I'm going to sneak over here and put an R. Boop, right there. Now I'm happy, okay? Two reactions we have to consider, okay? Now, do we have to consider the equilibrium when we have a strong acid? No, we don't have to do that. Here we are going to first do strong acid reactions. When you put an acid into solution and it is strong, the concentration of that acid that you're reading off a bottle is actually the concentration of H3O+. Let's look at that reaction down there and we see why. It is a one-way arrow, right? So everything that's on the left, all the HNO3 that you put in becomes the concentration of H3O+ and NO3-. Now, just to introduce this concept to you, you really don't have to use it for this problem. I want you to get an idea of what I'm talking about here with a table that I call an ICF table. This is not an equilibrium, so it's not an ICE table. It's a one-way reaction, and we know the acid donates, that's not an H, NO3-, and the water accepts that proton. So acid-base reaction is nothing more than a swap of the proton, okay? I want you to think about it this way. Instead of an E, I'm going to do an F for final. It doesn't go to equilibrium, it just goes completely. If I put in, as we see in this scenario, 0.20 molar, okay, and there's a lot of this. I mean, a heck of a lot. There's a lot of this. Before the reaction takes place, there's none of this and hardly any of this to where a 0 is okay to use. Now, it's not really 0. What is it? It's water, pure water. What is the value of this for pure water in terms of concentration? It's 1 × 10⁻⁷. Okay, so it's really tiny. You could write that in every time if you wanted to, but it's such a tiny number that it works for our problems just to say, yeah, there's a little bit in there, but it's not enough to worry about. Now, what we do in the change line is this reaction goes completely to products. All of it is going to get consumed, okay? And that leaves us with none. That's what a one-way arrow is telling me. Now, if we had a lot and a little bit of it reacts, we still have a lot, right? So I really don't have to put anything in underwater ever when I'm doing these problems. I can leave the water out. For every 0.2 of this that I reacted, I'm going to make 0.2 of this, and I'm going to make 0.2 of this. And so this is a way of doing a one-way reaction, okay, that we will utilize later. But maybe you don't need to do all this. If you know it's strong, whatever you put in, these become. So now, if we're trying to figure out the pH, what of this information do I need to know? Well, this is what I need to know. I need to know the concentration of H3O+, because pH is equal to the negative of the log of the H3O+ concentration. So all I have to do is plug in that 0.20, okay, and that will give me the pH. So if it's a strong acid, calculating the pH is pretty straightforward. You put in the concentration of the acid because its concentration is the concentration of H3O+. I don't want you to skip that step in your mind. Say to yourself, it's a strong acid, therefore concentration of the H3O+ is the same. And that's the is, that's italicized, capitalized, and underlined. That's why you put that number in. Okay? So that's a strong acid. So let's consider weak acids. Weak acids are not one way. What you put in here doesn't become this, because this equilibrium only goes this way to a limited extent. So we're going to have to do an ICE table, and we're going to maybe assume that x is small, if it's appropriate to do so, and solve for our variable. What we're going to see in this chapter is it's almost always appropriate, because the Ka values are so little, to do the approximation, the assumption that x is much, much smaller than your initial concentration. Students who start working through these problems and then they get ready to study for the test forget that assumption doesn't apply always, and they go back to do the former chapter where we're just introducing equilibrium. They start wanting to assume it every time. It's only when K's are small. So let's do an example of this one. I have hypochlorous acid, HOCl. Now it is asking me to calculate the pH of this solution. So I know at some point I need to know the H3O plus concentration so that I can get the pH. Whenever I'm trying to get the pH, that's the last step right before I get it. So let's write the reaction. You need to make sure you take the time to write the reaction. This is being dissolved, I put an AQ, into water, the liquid. It is a weak acid, therefore it's a reversible arrow. The acid donates, and when it does, it becomes OCl with a minus charge. I took an H plus off. This is aqueous, and I put it onto the water, and it makes H3O plus. Okay? And I am trying to calculate the pH, so I need to know this at, put an I, C, and an E here. I need to know this at equilibrium in order to get a pH. I need to know what sits right there. So let's see what I do know. I know initially, whenever they give you the concentration of the acid, that's what would be written on the bottle when you get it off of the shelf. That's not what it's in there right now, but when you prepare, you're preparing a solution that has 0.022 moles of this placed into enough water to make a liter of solution. So that's that. I don't have to put anything in here for the water. Initially, this is a 0. I put a 0 here, but we've talked about how that isn't really a 0. It's 1 times 10 to the minus 7 if it's at 25 degrees Celsius. All right. Anything else in that problem that I know? I know that the Ka value is 3.2 times 10 to the minus 8, and that's a real little value. Let's go ahead and write the expression. Ka for this reaction would be the OCl minus concentration times the H3O plus concentration divided by the HOCl concentration, okay? And I know all of that equals the value of the K that they gave me, which is 3.2 times 10 to the minus 8. Oops, 3.2. That doesn't look like a 2 at all. Let's try again. Sorry about that. She runs off screen, she comes back, she's got something to race with. All right, there we go. There we go, 3.2 times 10 to the minus 8. Okay, so that's what I know. That's what's given to me. That's how I'd utilize it. Okay, nothing else I can plug into my table, so here's where I'm stuck using a variable. I know some of this reacts. It's an equilibrium. Some of it will react, but not all of it. It's not like this. Only some of it reacts. For every one of those, I produce one of those and one of those. Okay? And so this is 0.022 minus x. This is x, and this is x. Now, I can't plug that into this expression. It's not, I don't know it yet. So I'm going to take all of this and put it into this piece. Okay? So I have got, I'll write it here, 3.2 times 10 to the minus 8 is equal to, well, this is x. This is x. So I'll call it x times x, which is x squared, divided by this, which is sitting right here, 0.022 minus x. Now, I don't want to use the quadratic equation if I can avoid it. So I look at this and say, can I avoid it? Well, when our k is real small, our x is real small. I'm not getting much of it reacting. So I assume, here's my assumption, we assume that x is much, much smaller than its initial concentration. What do I get to do if I'm making that assumption? Well, I can just ignore that x. I'm going to say it's so small that if I subtract it from 0.022, it's still 0.022. That makes it fairly easy to solve for. So what do? I take the 3.2 times 10 to the minus 8, and I'll come over here where I've got a little bit more room. 3.2 times 10 to the minus 8 times the denominator of 0.022. If I take this and multiply by that, that's going to give me x squared. But I want x, so I take the square root of both sides. Okay? And that will give me the value of x. X is equal to, and somewhere I've got the number, x is 2.7 times 10 to the minus 5. Now, you got to get in the habit of remembering that you assumed, and you should check your assumption. So is x, this is my x, much, much smaller than 0.022? Well, yes, this is 0.00027. Okay, moving it over 5 places. If I subtracted 0.00027 from this, I'll still get 0.022. So it is a good assumption. I've checked my assumption. Now, once I've solved for x, I always have to think, why did I find x? What do I want to know it for? I go back to the question. It says, calculate the pH. All right, so pH is the minus log of H3O plus. I know I need to know this. This is x. So H3O plus's concentration is 2.7 times 10 to the minus 5, right? That is the H3O plus. So now I'm ready to calculate the pH. pH in this problem here is the negative log of, where'd it go, 2.7 times 10 to the minus 7. So that's for the problem up there. And then I want to plug in for here, for this problem down below, minus the log of, where'd it go, 2.7 times 10 to the minus 5. And I get a pH of 4.58. All right. Now, this is a weaker acid, but look how small, how the pH is different. This was a strong acid. Its pH is less than 1. This is a weak acid. Its pH is much greater than 1, but it's still less than 7. So it's less than 7. It's an acid. It's not super low, so it kind of triggers in my mind that maybe we are talking about a weak acid here. So it's a legit value for this. Okay, so there is calculating the pH of a strong acid and calculating the pH of a weak acid. What's the big difference? Here, the strong acid, its concentration is the H3O plus concentration, which we can plug directly into it. For a weak, we must consider the equilibrium. We must put it into our equilibrium constant expression. We solve for x. We go back and figure out what that is for, and that will give us the value that we need to calculate the pH. Okay, so here's our next problem. We're just going to work several different ones. In this one, we're going to determine the Ka. Now, in the previous problem, we were given Ka, and we needed to get to the concentration at equilibrium to get the pH. So a reminder of 2 big common things that we can do with equilibria. If we know the K, we can get to the equilibrium concentration. If we know the equilibrium concentration, we can go to K. We're dealing in the world of Kas now, but that was true when we were dealing with just equilibria in general in our previous chapter. So in this case, we're going to determine Ka. So somehow I need to know the equilibrium concentrations in order to get the Ka. Now they give me the formula for formic acid. So this is HCOOH. That's formic acid. So that's an organic acid again, and it's this hydrogen that's donatable. So that gets placed in water, and you ask yourself, is that on the strong acid list? Well, it's not. So that tells me I need to do reversible arrows. Remember, you always have to write your own reactions when you're dealing with this acid-base chapter, and it's just a proton swap. So we have HCOO minus, and we have water accepting that proton, and its conjugate acid is H3O plus. Okay, now I want to leave room for a table underneath it, but since I know I'm trying to calculate Ka, I'll go ahead and write the expression. It is HCO minus concentration, H3O plus concentration in the numerator, right? And it is HCOOH in the denominator. And if I knew all of those at equilibrium, I'd know my Ka value. I don't know all those yet, but if I set myself up an ICE table, maybe I could get there. All right, what do they tell me? They tell me how much formic acid was dissolved in water enough to make 1 liter. So I was given 0.25 divided by 1. That's the concentration, okay? I don't care about water, so I'll leave it out. And this is 0, and this is essentially 0, okay? Then I go through there, and they tell me one other piece of information. They tell me the pH of the solution. Now, somehow I'm going to be able to use that, but let's figure out. See, if we got stuff in here, there's nothing about pH that gets plugged into anything I see here. But I know that if I had pH, I could get the H3O plus concentration. So you stop and get the pH. I'm sorry, you know the pH. Get the H3O plus concentration from that number. All right, hopefully you saw that you got that right, but how did you get it? H3O plus concentration is 10 to the minus pH. And so the value for that will be 0.00646. Now I'm carrying an extra significant figure along. It's 0.0065 to the number of decimal places that I really know it. But there we have that. All right, now how in the world do I put that somewhere in here? Well, this is the H3O plus concentration. I measured the pH after the establishment of the equilibrium, so I can put that into my table right here. A lot of students will just take off and start blindly putting X's into this table because they're used to putting X's into their ICE table. I don't need to put any variables in here. I can fill it up with real numbers as soon as I put that there, because if I started with nothing and I produced this amount, then I know my change line was this amount. And the change line is this reaction taking place, so I can look at my coefficients. So I must have produced the same amount of this, which carries down to here. Now, if I produce this, what happened on this side? It got consumed, minus 0.00646. And when I take these numbers and I subtract them, I get 0.24, looks like 4 maybe. Now I only really know it to 2 decimal places there. Oh no, it's not 4. According to this, it's 3. Well, I don't know. 646. All right, I know what happened. I subtracted in one place, it rounded, in the other it didn't. All right, so there we have it. I really only know it's 2 decimal places, but it is changing it a little bit. All right, so now I want to go ahead and carry extra sig figs along for the ride because I like to do that and not round until the very end. So I'm ready to plug in my E line into this expression. So I have 0.00646 times 0.00646 divided by 0.2434. You need to know all of these numbers in order to get a Ka value. And the Ka value for this is 1.7 times 10 to the minus 4. Since it's a weak acid, we expect a negative power. Weak acids don't lie very far to the right at all. They have way more, thousands of times more of this form than they do those forms. Okay, so that is how to determine a Ka value. All right, let's define something. Let's define something called percent ionization. Sometimes when we're talking about acids, we will talk about the pH of the solution. But there's another common term that we talk about with acids, and that is its percent ionization. It is another way of telling us how far does this thing lie to the right. Small k's means it doesn't lie very far to the right, and that's one way of knowing it. But percent ionization is another way, so let's define it. Percent is always the part over the whole, okay? So the part is the part that ionized. What part of it is in the ionized form? The whole is how much did you put in there. It's the initial amount. That would be both this and this form at equilibrium. It is the whole, okay? Percent is always the part over the whole times 100. It's percent ionization, so we want to know the ionized over the whole. the ionized at equilibrium over the whole. Now, because the way this pans out here, the concentration of H3O plus is equal to the concentration of that. So you could use that instead, H3O plus's concentration over, now notice that little that little circle after the HA. That's its initial. It is the whole, it is everything, okay? So we did a problem with the 0.022 molar HOCl, okay? We did that problem earlier, and we came up with an, at the E line, okay, that the OCl minus concentration, which is equal also to the H3O plus concentration, we saw that those values in that problem were 2.7 times 10 to the minus 5. So we're not going to do all that work again, but we set up an ICE table for that reaction, and we came up with this molarity. But they want to know the percent ionization and not the pH. So the way you would do the percent ionization is you take your concentration of H3O plus, which is 2.7 times 10 to the minus 5, and you divide by the initial concentration of the acid, which is always what they give to you, unless they tell you otherwise. When they say the concentration of the acid is, and they give you a number, they're telling you the initial concentration of that acid. So then you do times 100. Okay? And so that will give us the percent ionization, and it is a really measly 0.12%. So this acid only less than 1%, only 0.1% turns into this. The rest of it stays there. So when I say a weak acid, we're talking it's either 100% or it's much, 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 much less than 100% for most of them. All right, that's my check, and yep, got that answer. Okay, now pH changes with concentration, okay? You take a weak acid, if you add more, the pH is a little lower, you add less, it's a little higher. Percent ionization also changes with concentration, so let me move to the screen here, and let me show you what would happen with a weak acid. The green line is a strong acid. So whether you had just a little bit, and let's say we had 0.01 molar of that acid, it would 100% ionize. So every bit of the acid we put in there, if it's strong, 100% will go to form the ionized form, and so we say that it is 100% ionized when it's a strong acid. If I had a 4 molar solution, okay, a 4 molar solution is still 100% ionized. That's the definition of strong acid. But weak acids are not that way. Weak acids drop off pretty rapidly. If I put a smidgen, and let's say I put just 0.00001 molar solution of a weak acid, it would be up, oops, shoot, it disappeared on me. It would be up here in the almost 100% range, and then it drops off very rapidly and then slowly decreases, okay? So the pH changes with concentration, the percent ionization changes with concentration. It will ionize less and less the more you put in there, okay? The more acid you put in there, the less percent ionization it has. pH will still go up because you're adding more acid, but the percent of them that actually ionize drop off. All right, so what we got to look at next is what to do if we have a mixture of acids. So we're going to take multiple acids and add them together, and we're going to be able to calculate the pH of those mixtures as we go to our next lesson.